39 seconds. That's the whole story, and it's two completely different stories. On the 24th of June, 2026, the ground under northern Venezuela tore open, a magnitude 7.2, and then, 39 seconds later, before anyone could even understand what the first one was, a second rupture, a magnitude 7.5, two of the strongest earthquakes that country had felt in over a century, back to back, in less time than it takes to read this sentence out loud. For the people standing on top of it, those 39 seconds were a curse, just long enough to feel the first wave of terror, not long enough to do anything about the second. Now hold that number in your head, 39 seconds, because on that exact same day, on the other side of the Caribbean, on American soil, a different fault slipped, smaller, a magnitude 5.6 in Northern California, and in that case, 30-something seconds became a gift. Phones across the state lit up before the shaking arrived. A warning, a countdown, time to drop, to brace, to stop. Same day, same planet, two faults, two versions of the same handful of seconds. One country got blindsided, the other got a head start. And the difference between those two outcomes is not luck. It's a machine. A machine that took the United States almost 40 years and hundreds of millions of dollars to build, that just reached a quiet milestone almost nobody reported. And that has one terrifying blind spot sitting right off the coast of the Pacific Northwest. By the end of this video, you're going to understand exactly what happened in those 39 seconds in Venezuela, exactly how a wall of water ended up threatening Puerto Rico and the US Virgin Islands, exactly how California outran an earthquake the same afternoon, and why the one quake Americans should fear the most is the one this whole system still can't see coming. You'll understand the science, the history, and the part almost no one is talking about. This is the Horizon Lab, where the truth is usually more unsettling than the conspiracy. If you want calm, accurate breakdowns of the forces shaping our planet, subscribe and stay with us. And do me a favor, tell me in the comments where you're watching from and whether your phone is set up to warn you. You'll understand why that matters by the end. Let's get into it. Start with Venezuela, because the timeline is almost hard to believe. At 22:04 and 33 seconds Coordinated Universal Time, the US Geological Survey logged a rupture about 23 kilometers southeast of a town called Yumare, magnitude 7.2. On its own, that is a major earthquake. The kind that makes global headlines for days. The kind that levels buildings. But it wasn't on its own. 39 seconds later, 22:05 and 11 seconds, a second rupture, 16 kilometers southwest of the city of Morón, about 10 kilometers down. Magnitude 7.5, bigger than the first. And here is the part that matters. In earthquake science, the first one is now called the foreshock, and the second one the mainshock. The smaller quake didn't relieve the pressure. It pulled the trigger on something larger right next door. Both of these ruptures happened along the San Sebastián fault system. If that behavior sounds familiar, it should. This is a strike-slip fault, where two slabs of crust grind past each other sideways. It is, in plain terms, Venezuela's version of the San Andreas. The same geometry, the same grinding, the same capacity to store decades of strain and release it in seconds. How rare was this? You have to go back to the year 1900 to find a Venezuelan earthquake this strong, a century of relative quiet, and then two giants in under a minute. The US Geological Survey runs a system called PAGER that estimates the human and economic damage of a quake within minutes. For both of these events, PAGER lit up red. Red is the top of the scale. Red means high casualties and an event the region simply cannot absorb on its own. And the early numbers backed that up. By late June, the confirmed death toll had climbed past 900, with thousands injured, and it kept rising in the days after. I want to be honest with you about those figures, because this is exactly where a lot of channels get it wrong. In the first hours and days after a disaster like this, the numbers are estimates. They move. They are almost always revised upward as rescuers reach collapsed buildings. So when you see a death toll in the first week, treat it as a floor, not a final count. The truth, sadly, is usually worse, and it arrives slowly. What made this so deadly wasn't just the size. It was that combination. A foreshock that frightened people but gave them no real time, followed by a stronger shock while they were still reacting. 39 seconds is enough to feel fear. It is not enough to evacuate a building, and no warning system on Earth was going to give those people more than that, because the warning would have to outrun a quake that was already underneath them. Which raises the obvious question. If the shaking was the disaster in Venezuela, why did the United States, 1,000 kilometers away, suddenly find itself staring at the sea? Here's what most people outside the Caribbean never heard. 8 minutes after that main shock, at 22:12 Universal Time, the National Tsunami Warning Center issued a tsunami advisory. Not for Venezuela, for Puerto Rico, for the US Virgin Islands. For the British Virgin Islands, American territory and American citizens were suddenly on a tsunami clock because of a fault that ruptured off the coast of South America. Let me explain why that's surprising, because it gets to something important about how these threats actually travel. I told you the San Sebastián fault is strike-slip, sideways motion, and here's a rule of thumb you'll hear from seismologists. Strike-slip faults are usually bad tsunami generators. To shove a wall of water into motion, you generally want the seafloor to move up or down, vertically, like a paddle. Sideways grinding doesn't do that as efficiently, so in theory, this should not have been a major tsunami threat. So why the advisory? 2 reasons, and both are the reason warning centers exist. First, no fault is purely sideways. Real ruptures along curved, messy fault systems almost always have some vertical component, especially near the coast where the geometry bends. Even a small vertical shove from a magnitude 7.5 can launch a wave. Second, and this is the key one, a tsunami advisory is not a prediction that disaster is coming. It is a statement that they cannot yet rule it out, and that you should get off the beach and out of the water until they can. An advisory is the system buying time to be sure. The default is caution, because the cost of waiting to be certain is measured in lives. In this case, the ocean cooperated. The tide gauges and the deep ocean buoys, the ones that sit on the seafloor and feel a tsunami pass overhead, didn't register dangerous waves. Within the same evening, the advisory was cancelled. No damaging tsunami reached Puerto Rico or the Virgin Islands. But sit with how close that felt. For a few hours, the same event that was killing people in Venezuela had American coastlines watching the water. And it's a preview of something much larger, because the Caribbean is genuinely one of the most underappreciated tsunami zones touching the United States. In fact, just before this happened, the US Geological Survey had published its first updated seismic hazard model for Puerto Rico and the Virgin Islands in over 20 years, the first major update since 2003. And that model raised the maximum expected magnitude for certain quakes in that zone to a full magnitude 8. The science was already saying, on paper, that this region is more dangerous than we used to think. Then the ground proved the point. So that's the threat that travels. Now let's go back to that same afternoon, to the west coast of the mainland, and watch the United States do something Venezuela never had the chance to do. Get a warning out before the shaking started. Rewind a few hours to earlier on that same 24th of June and move about 5,000 miles northwest. Mendocino County, Northern California. Wine country, redwoods, a stretch of coast that most of the country never thinks about. At 3:10 in the afternoon, Universal Time, a fault 11 kilometers north of a place called Redwood Valley let go. Magnitude 5.6, about 10 kilometers deep. By the standards of what we just described in Venezuela, modest. Nobody died. It wasn't a catastrophe. But here's why it matters more than its size suggests. That part of California is one of the most seismically active corners of the lower 48, sitting near the northern end of the San Andreas system, right where it dives offshore. People felt it. The US Geological Survey estimates roughly 80,000 people experience strong shaking, in the range that rattles dishes off shelves and cracks plaster, and that close to 10 million people across Northern California felt it to some degree. And before most of them felt a thing, their phones went off. According to the governor's office, the Shake Alert system pushed an earthquake warning to more than 1 million Californians. 1 million. Before the shaking arrived at their location. Let me say that again, because it's the whole point of this video. The earthquake happened, the system detected it, calculated it, and fired off alerts that physically outran the destructive waves of the quake to over 1 million phones. People got a buzz, an alarm, a screen that said earthquake, expect shaking, drop, cover, hold on, seconds before the floor moved. Now think back to Venezuela. 39 seconds of curse. People feeling the first quake with no idea a bigger one was 39 seconds behind it. And then think about Mendocino, seconds of grace. A warning that beat the wave to the destination. That is not a difference in the earthquakes. A 5.6 is not gentler to the people standing on top of it than a 7.5 is. Not in those first violent seconds. The difference is entirely a difference in what was built underneath the society before the quake ever happened. One country had a machine listening to the ground, fast enough to send a message faster than the earth could send a shockwave. The other didn't. So how do you possibly warn someone about an earthquake before it reaches them, when the earthquake itself is the fastest messenger in the room? How do you outrun the ground? You don't. You outrun one part of it. And to understand how, you need to understand that an earthquake isn't one thing arriving, it's a race between two. An earthquake doesn't send one signal, it sends two, and the entire trick of earthquake early warning lives in the gap between them. When a fault ruptures, it releases energy as waves that travel out through the rock. The first to arrive is called the P wave. The P stands for primary because it gets there first. It's a compression wave, the rock squeezing and stretching in the direction the wave travels, and it moves fast. Something like 6 kilometers every second through the crust. Here's the good news about the P wave. It's quick, but it's relatively gentle. It rattles, it rarely destroys. The destruction comes from what's behind it. The S wave, S for secondary, and the surface waves that follow. These move slower, closer to 3 or 4 kilometers a second, and they shake the ground side to side and up and down. That's the motion that snaps columns and collapses freeways. The dangerous part of an earthquake is literally the slow part. So picture the rupture as a starting gun. 2 runners leave the line at the same instant. The P wave is the sprinter, out front, harmless. The S wave is the heavyweight, lagging behind, carrying all the damage. Now here's the move. Shake alert puts sensors in the ground all over the west coast. The instant the P wave passes the nearest sensors, computers grab those first few seconds of data, estimate where the quake started and how big it's becoming, and fire an alert. And that alert doesn't travel through rock. It travels through the cell network, through the internet, at the speed of electronics, which is, for all practical purposes, the speed of light. So you have a slow, destructive wave crawling through the ground at a few kilometers a second, racing against a warning, moving at the speed of a text message. Over enough distance, the warning wins. The message arrives, your phone screams, and the shaking shows up a few seconds later. You already know this physics, by the way. You've felt it your whole life. Lightning and thunder. You see the flash instantly, then you wait, and the boom rolls in after. Same idea, flipped. The light is the warning, the thunder is the shaking. The farther away the strike, the longer the gap, the more time you have to flinch. And that comparison reveals the catch, the one we'll come back to. The closer you are to the lightning, the shorter the gap. Stand right under the strike, and the flash and the boom hit together. There's no warning to give. It's the same with earthquakes. There's a zone right around the epicenter where the warning simply can't outrun the shaking, because you're too close, because the waves reach you before the math is even finished. Seismologists call it the blind zone. If you're sitting on top of the rupture, the system can't save you. It can only warn the people farther out. In Mendocino, most of those 1 million Californians were far enough away to get their seconds. Hold on to that idea of the blind zone. Because there is one specific earthquake, the one that frightens seismologists more than any other in this country, that puts almost an entire coastline inside it. We'll get there. But first, you should understand that this machine didn't appear overnight. The United States paid for it in disasters, and the bill came due on an October evening in 1989 in front of 60,000 baseball fans. October 17, 1989, Candlestick Park, San Francisco. Game 3 of the World Series. The Athletics against the Giants. 60,000 people in the stands, millions more watching on television, waiting for the first pitch. At 5:04 in the afternoon, the broadcast cut out. A magnitude 6.9 earthquake had ruptured on the San Andreas fault system near a peak called Loma Prieta in the Santa Cruz Mountains. The shaking lasted only about 15 seconds, but in those 15 seconds, it reshaped how the United States thinks about earthquakes. A double-decker section of freeway in Oakland pancaked. The upper deck dropped onto the lower deck, crushing cars in between. A piece of the Bay Bridge collapsed. Fires broke out in the Marina district. When the counting was done, around 63 people had died and thousands were injured. The fact that it happened during a World Series, with the whole country watching, burned it into the national memory in a way that a quiet quake never could. And here's the lesson the scientists took from it. Loma Prieta wasn't even the big one. A 6.9 is serious, but the San Andreas is capable of far worse. If a 15-second, magnitude 6.9 could do that to the Bay Area, what would the real event do? And, the harder question, could we have done anything in those 15 seconds if we'd seen it coming? That question, asked over and over after Loma Prieta, and then again after the Northridge quake in 1994, is the seed of everything we're talking about. The United States started pouring money and science into a single goal: build a network of sensors dense enough and computers fast enough to detect a quake in its first seconds and warn people downstream before the shaking arrives. It did not happen quickly. This is the part people don't appreciate. Earthquake early warning took decades. The science had to mature. The sensors had to be installed, hundreds and hundreds of them, wired into a system that never sleeps. Japan and Mexico got their public systems running first. The United States lagged, partly because of cost, partly because covering an entire active coastline is an enormous undertaking. The public version of Shake Alert finally went live in California in 2019. 30 years after Loma Prieta. 30 years. Then it expanded to Oregon and Washington in 2021. And for years after that, engineers kept doing the unglamorous work, installing the last stations, filling the gaps, making the network dense enough to actually trust. And just a few weeks before those quakes in June, that decades-long project quietly crossed a finish line almost nobody outside the field even noticed. A milestone that, for the Pacific Northwest, changes everything. On the 4th of June 2026, the University of Washington and the Pacific Northwest Seismic Network announced something that should have been front-page news from Seattle to San Francisco. The Shake Alert sensor build-out for the Pacific Northwest was complete. Every single one of the planned stations, 569 seismic stations installed across Washington and Oregon, the full network the system was designed to have. For the first time, the west coast of the United States, from the Mexican border to the Canadian border, was covered by a finished earthquake early warning sensor grid. Let me put that in human terms. For years, the Pacific Northwest had Shake Alert, but with holes in it. Imagine a smoke detector system in a giant building where a third of the detectors hadn't been installed yet. It works, but there are rooms where a fire could get going before anything notices. Filling in those last stations means the system can now detect a quake faster, locate it more precisely, and size it more accurately, because more sensors feel the P wave sooner and feed more data into the math in those critical first seconds. More sensors equals faster detection equals more warning time for everyone downstream. In a technology where the entire product is measured in seconds, density is everything. Every station you add can shave a fraction of a second off detection, and a fraction of a second of warning, multiplied across millions of people, is a meaningful number of injuries prevented. This is genuinely good news, and I want to be clear about that, because this channel does not exist just to frighten you. This is one of the great quiet successes of American earth science. A multi-decade, multi-state engineering project, started in the grief after Loma Prieta, finished on a Wednesday in June with almost no fanfare. The same system that warned 1 million Californians in Mendocino now stands complete across the entire West Coast. So you'd think the story ends there. The shield is finished. The coast is covered. Sleep easy. It doesn't end there. Because completing the network exposed, in sharp relief, two problems that no number of land-based sensors can fully solve: And these two problems are the reason a seismologist can look at 569 brand new stations and still lose sleep. The first problem is about a number. Specifically, it's about the system getting that number wrong at the worst possible moment. And the world already watched it happen once, on a scale that killed almost 20,000 people. Here's an uncomfortable truth about earthquake early warning. The system has to guess how big the quake is while it's still happening, and for the largest earthquakes on Earth, the kind that matter most, it has historically guessed too small. This is a problem with a technical name, magnitude saturation. And to understand it, you have to understand that a giant earthquake isn't an instant. It's a process that unfolds over time. A small quake ruptures a small patch of fault, and it's over in a second or two. But a magnitude 9 doesn't work like that. The fault unzips. The rupture can run for hundreds of kilometers, and it can take minutes, not seconds, to finish tearing, which creates a brutal problem for a warning system whose entire job is to act in the first few seconds. In those first seconds, a magnitude 9 and a magnitude 7.5 look almost identical. They start the same way. The difference only shows up later, as the giant just keeps going and going, long after the system has already made its call. So the early estimate clips. It saturates. The traditional sensors, which measure how fast the ground is shaking, get overwhelmed and tend to lock in a number that's far too low for the truly enormous events. You don't have to imagine what that looks like, because it already happened in the most studied earthquake in modern history. The 11th of March 2011, off the coast of Tohoku, Japan. Japan has the best, fastest, most expensive earthquake warning system on the planet. And when that quake struck, the initial estimate badly undersized it. The first warnings went out based on a magnitude in the high 7s to low 8s. The reality was a magnitude 9.0. That gap is not small. The energy roughly doubles with every small step up in magnitude, so the difference between an 8 and a 9 is enormous, dozens of times the energy. And it had a consequence. Because the quake was sized too small at first, the initial tsunami forecast for parts of the coast was too small too. People were told to expect a wave far lower than the one that actually came. Around 19,000 people died, the overwhelming majority of them not from the shaking, but from the water that followed. A warning system fired, did its job at lightning speed, and still got the single most important number wrong, because the physics of giant quakes hides their true size in those opening seconds. So how do you fix it? You stop relying only on how fast the ground shakes, and you start measuring how far the ground actually moves and stays moved, permanently. That's what high-rate GPS does. The same satellite positioning in your phone, but precise and fast enough to track the ground physically shifting in real time. A giant quake permanently moves the land, sometimes by meters. A shaking sensor can saturate, but a GPS station that watches a coastline lurch 4 meters to the east and stay there cannot mistake that for a small quake. It is direct, physical proof of an enormous rupture. The US Geological Survey has been working to weave high-rate GPS into Shake Alert for exactly this reason, to catch the giant that traditional sensors would undercount, to make sure that when, not if, but when, the truly massive quake hits the west coast, the system sizes it correctly in time to matter. And which quake is that? Which is the giant the whole system is bracing for? It's the one hiding in the one place all 569 of those beautiful new sensors can barely see. Offshore. This is the part almost no one talks about, so let me make it as clear as I can. Run your eyes up the west coast on a map. California, Oregon, Washington. Now look just offshore, out under the Pacific, running roughly from Northern California all the way up past Vancouver Island, about 1,000 kilometers of it. That's the Cascadia subduction zone, and it is, without much competition, the most dangerous fault in the continental United States. Here's why it's different from the San Andreas. The San Andreas is a strike-slip fault, 2 plates grinding sideways, the kind we saw in Venezuela. Cascadia is a subduction zone. That means one tectonic plate, the Juan de Fuca, is being shoved down and under the North American plate. The two are locked together, jammed, building strain for centuries. And when a locked subduction zone finally lets go, it doesn't produce a magnitude 7. It produces the giants. Magnitude 9. The same kind of quake that struck Tohoku, the same kind that undersizes warning systems and launches tsunamis tens of meters high. A full-margin Cascadia rupture would be the worst natural disaster in modern American history. The shaking could last not 15 seconds like Loma Prieta, but 4, 5, even 6 minutes, long enough to bring down old buildings and bridges across Seattle and Portland. And minutes after the shaking stops, a tsunami would come ashore along the entire coastline of Oregon and Washington. So now, the whole point of this video, we just built a complete, finished, 569-station early warning network across exactly this coastline. Surely that's the answer. Surely Cascadia is the one we're most ready for. Here is the cruel part, the thing that should keep you up at night. Every one of those sensors is on land, and the Cascadia fault is offshore. It ruptures out under the ocean, dozens of kilometers from the nearest sensor on the beach. Remember the lightning and thunder. Remember the blind zone, the area right around the rupture where the warning can't outrun the shaking because you're too close. For a quake that starts offshore, the entire coastline sits inside that blind zone. The communities on the Oregon and Washington coast, the ones who would face the tsunami first and fastest, are the ones who would get the least warning, or none at all. The shaking would be their warning. By the time the system on land confirmed the giant, the people who needed the seconds most would already be in them. The cities inland, Seattle, Portland, Tacoma, would still get precious time, tens of seconds, because they're farther from the offshore rupture. That's real, and it matters. But the coast itself, the front line, is largely blind. This is the answer to the question I asked you at the very start. Why did one country get blindsided while the other got a head start? And why can't the warning save the place that needs it most? Because the warning is a foot race, and you can only win a foot race if you have a head start. Put your starting line offshore, in the deep water, dozens of kilometers from your nearest sensor, and for the closest coastline, there is no head start left to give. We didn't build the network in the wrong place. We built it everywhere we could stand. The problem is that the most dangerous fault in America doesn't run under our feet. It runs under the sea, and so far, that's where our eyes stop. The good news? This problem has a solution. We know exactly what it is, because another country, sitting on the very same kind of fault, already built it. After Tohoku, Japan did something the United States has not yet done. They put their sensors in the ocean. It's called SNet. Picture a web of seismometers and pressure sensors, not bolted to the land, but laid out across the seafloor itself, off the northeast coast of Japan, connected back to shore by cables running along the bottom of the Pacific. Roughly 150 stations, sitting directly above the subduction zone that nearly destroyed the country in 2011. Think about what that changes. Instead of waiting for a quake's waves to swim dozens of kilometers from the offshore rupture to the nearest land sensor, the sensors are already there, right on top of where the rupture happens. They feel it first, and those seafloor pressure sensors do something land seismometers can't. They can detect the tsunami itself, the actual bulge of water, as it passes overhead in the open ocean, long before it reaches the coast. The land network warns about the shaking. The seafloor network can confirm the wave. For a country facing a subduction zone giant, that's the difference between guessing and knowing. Offshore sensors shrink the blind zone. They move the starting line out toward the rupture, so even the coastline gets at least some head start. They help solve the magnitude saturation problem too, because they're measuring the giant from right on top of it. It was not cheap. A system like SNet runs on the order of $100 million and more, plus the cost of maintaining hardware that sits corroding under kilometers of seawater in one of the most punishing environments on the planet. But Japan looked at 19,000 dead and decided the alternative was more expensive. And in the United States, this is where it stands. The science community knows exactly what's needed. Researchers and the US Geological Survey have been openly pushing to extend monitoring offshore into the Cascadia zone, with ocean-bottom seismometers and seafloor sensors modeled on what Japan proved works. The same week the Pacific Northwest Network was declared complete on land, scientists were already saying out loud that the next frontier is the water, that a finished land network is a milestone, not a finish line, that the coast is still exposed. But offshore monitoring at the scale Cascadia demands does not exist yet. It is proposed, it is studied, it is, in places, beginning. It is not built. And every year it isn't built is another year the Pacific Northwest coast is one offshore rupture away from a tsunami it would barely see coming. So we have a complete system that protects the inland cities well, the coast poorly, and that everyone working on it knows is only half finished, because the other half lives under the sea. Now, how do we know Cascadia really does this? How do we know it produces the giants and the waves when no one alive has ever seen it happen? Because it left us a receipt, written on 2 continents more than 300 years ago. For a long time, scientists genuinely weren't sure the Cascadia fault could produce a great earthquake at all. It was quiet, too quiet. No giant quake in any written American record. Maybe, some thought, it just creeps along harmlessly. The truth turned out to be hiding in the trees and in a library halfway around the world. Walk certain estuaries along the coast of Washington and Oregon, and you'll find them. Ghost forests. Stands of dead western red cedar, grey, bare trunks still standing in tidal marshes, killed where they grew. Scientists studied the rings and the soil and pieced together what happened. The land had suddenly dropped. In a single event, a stretch of coastline lurched downward by a meter or two, and the sea rushed in, drowning whole forests in salt water and burying them in mud. Only a massive earthquake, a subduction zone giant, drops a coastline like that all at once. Tree rings could date it to the dead of winter, around the year 1699 to 1700, but to pin it down to the day, they needed a witness, and the witness was in Japan. In Japanese village records from that era, there are accounts of a tsunami, a wave that came ashore along the Pacific coast of Japan and flooded homes and fields. What made it strange, what the historian who connected this called the orphan tsunami, is that it arrived with no parent, no earthquake. The Japanese felt no shaking before it, a wave out of a calm sea. A tsunami with no local quake means the quake happened far away, across the ocean, and the wave traveled all night to arrive. Working backward from the Japanese records, the timing, the wave height, the arrival, scientists could calculate the size and the moment of the earthquake that must have caused it. The answer pointed straight back across the Pacific, to Cascadia, to a rupture estimated around magnitude 9, on the evening of the 26th of January in the year 1700. Sit with that. We know the date of an earthquake that struck before the United States existed, that no one wrote down on this continent, because the wave it sent registered in Japanese village ledgers 10 hours and 4,000 miles later. The ghost forests told us it happened. The orphan tsunami told us exactly when. And it tells us something else. These giants come back. The geologic record, the layers of tsunami sand stacked in coastal marshes, suggests Cascadia has produced great earthquakes roughly every few hundred years, on average, though irregularly. The last full one was in 1700. That's more than 300 years ago. This is not a prediction. No one can tell you the year, and you should walk away from anyone who claims they can. But the clock is real, it is old, and it is running. The fault that drowned those forests is still locked, still loading, still offshore, still, for the coast, mostly out of sight. Which brings us to the question of what these warnings are really for. What 39 seconds, or 10, or 0 actually buys a human being? Because there's a reflex, when people first hear about earthquake early warning, to scoff. 10 seconds? 30? What good is that? You can't evacuate a city in 30 seconds. You can't even leave a building safely. So why bother? Here's the answer, and it reframes everything. Earthquake warning was never about running away. It's about the things that can happen automatically, in seconds, that save lives, without anyone deciding anything. In those seconds, before the shaking arrives, here's what a warning can trigger. Trains and high-speed rail automatically brake and slow down, so they're not taking a curve at full speed when the tracks start to move. That single measure has prevented derailments. Surgeons get a signal to lift the scalpel away from the patient. Factories pause delicate processes. Elevators stop at the nearest floor and open their doors, so no one is trapped between floors when the power cuts. Fire stations roll their truck bay doors up, so the doors don't jam shut and trap the engines inside. Gas valves can shut, and gas is what turns an earthquake into a firestorm. Remember, after Loma Prieta, it was fire in the Marina district. And for an ordinary person, those seconds buy the single most effective thing you can do in an earthquake. Drop, cover, and hold on. Get under a sturdy table, get away from windows. Most earthquake injuries aren't the building collapsing, they're people being hit by falling objects, or cut by glass, or hurt trying to run while the floor is moving. A few seconds of warning is enough to stop, drop, and protect your head before any of that starts. It is the difference between being caught standing and being braced. That's what those 1 million Californians in Mendocino received. Not a chance to flee, a chance to brace. Multiply a few seconds of bracing across 1 million people, and you prevent a real, countable number of injuries and deaths. That's the product. Seconds converted into safety automatically. Now turn back to Venezuela, where there was no such system, and you see the human cost of the gap in sharp relief. The response there was not seconds of automated bracing. It was days of digging, international search and rescue teams mobilizing. In the United States, the response to a foreign disaster of that scale kicks in fast. US Southern Command moved naval assets and military airlift toward the region. American urban search and rescue task forces, the same elite teams that deploy after domestic disasters, prepared to assist. A major aid package was announced, on the order of $150 million. That is what the absence of warning looks like on the back end. When you can't give people seconds before, you spend weeks and fortunes after. So when someone asks what good are a few seconds, the honest answer is, they are one of the highest return investments in public safety ever engineered. The trick is, you have to build the machine before the quake, not after. And you have to be honest about what it can and can't do. Which brings us to the part of this story where the truth runs head-on into the myths. If you spend any time online searching earthquakes, you are going to run into a wall of confident nonsense. So let's clear it out, carefully, because the truth here is more useful than the fiction. Myth number 1, the big one, that earthquakes can be predicted. That someone, somewhere, can tell you a magnitude 7 will hit a specific city on a specific date. They can't. Not the US Geological Survey, not any government, not any scientist, not any app, not any animal. Here's the crucial distinction this entire video has been built on. Prediction and warning are not the same thing. Prediction means naming the quake before it happens. That is not possible with current science. Warning, what Shake Alert does, means detecting a quake that has already started and racing a message ahead of its waves. One is science fiction. The other is the real working machine we've been describing. Anyone who blurs those two is either confused or selling something. Myth number 2. The doomsday fish. You'll see it every time a big quake hits. A rare, ribbon-like deep-sea oarfish washes ashore, and the headlines scream that it's an omen, that the fish predict earthquakes, rooted in old folklore. Scientists have actually studied this, looked at strandings against earthquake records, and found no reliable connection. Deep-sea fish wash up when they're sick or dying or caught in currents. A stranded oarfish tells you a fish is having a bad day. It tells you nothing about the fault. Myth number 3, that a great quake will crack California off and drop it into the ocean. It won't. The San Andreas is a strike-slip fault. The two sides slide past each other horizontally. Over millions of years, Los Angeles is slowly creeping northward toward San Francisco, but nothing detaches and sinks. California is not going anywhere. The real threat isn't a continent falling into the sea. It's the shaking, and on the coast, the wave. Now, where is there real scientific debate? Because honesty cuts both ways. Scientists can't predict a specific quake, but they can and do calculate probabilities. After a large quake, they issue aftershock forecasts, the odds of another strong shock in the coming days, using well-tested statistical models. That's why a foreshock like Venezuela's matters. It briefly raises the probability that something bigger is coming, which is exactly what happened in those 39 seconds. That's not prediction, that's probability, stated honestly, with the uncertainty attached. So here's where it all lands. The conspiracy version says someone, somewhere, secretly knows the date and isn't telling you. The truth is so much heavier than that. No one knows the date. No one can. The fault offshore is locked and loading and silent, and the most advanced warning system ever built can give the inland cities seconds and the coastline almost nothing. There's no secret cabal in control. That's the unsettling part. Nobody is in control. There is only the ground, the clock we can't read, and the seconds we've managed to engineer for ourselves. So let's bring it home. On one day in June, the planet showed us both versions of the same handful of seconds. In Venezuela, 39 seconds were a trap, the gap between a foreshock and a giant, with nothing built to use them. Off the coast of Puerto Rico, the sea was watched and held its breath and let us go. And in Northern California, 1 million people's phones lit up before the ground moved, because for 30 years this country has been building a machine to turn the physics of an earthquake against itself. That machine is now complete across the entire west coast on land. That's the triumph. And it still cannot protect the one coastline facing the deadliest fault in America, because that fault sits offshore, in the blind zone, in the water where our sensors don't yet reach. That's the unfinished work. Both of those things are true at once. Here's the one practical thing I want you to take from this. If you live anywhere on the west coast, or really anywhere earthquakes happen, those warnings are already available to you, and most people never turn them on. Check your phone's settings for earthquake alerts. On many phones it's built right in, and there are official apps tied into Shake Alert. It costs you nothing, and one day it might hand you the seconds you didn't know you were owed. The seconds to stop, to get under the table, to protect your head. Do it today, not after. And then there's the bigger question this leaves open, the one we can't answer yet. We know Cascadia ruptured in 1700. We know it produces magnitude 9s. We know the clock is more than 300 years old and running. What we don't know is the year, and we never will, until the morning the ground itself tells us. The only honest position is to be ready, and to keep pushing those sensors offshore before the giant arrives, not after. If this changed how you think about that little earthquake alert setting you've been ignoring, subscribe, because we go to these places carefully and without the hype. And if the Cascadia fault is the one that unsettled you, that locked offshore monster 300 years overdue, then watch this next. We pulled apart exactly what the first 6 minutes of a full Cascadia rupture would do, hour by hour, from the first tremor to the moment the wave reaches the shore. The seconds run out fast in that one. I'll see you there.